Let's look again at this video and consider what's going to be rotating. We have the platform, what's in black here, and we have the strings, but then we have two toys, this bluish toy, bluish and orange toy, and then we have another toy that's hidden here that will come into play once we start playing the video. Here we go. Okay, you notice as the platform rotates, everything that we see on the platform rotates at the same angular velocity. In other words, omega is the same for all of them. But then let's pay attention to the toys. The smiley face and this bluish toy. Notice that for the smiley face, the radius for its rotation is this much, from here to the center of the platform. However, for the bluish toy, the radius of the circle it rotates about is this much. Okay, when you consider these radii, think of how much each one of them moves at every rotation. The smiley one, or whatever it is, this orangish toy, for every rotation, it's going to move a distance equal to the circumference of this large circle. However, the bluish is going to move this distance. So for the same amount of time, the orangish toy is going to move a distance that is larger than the bluish toy. It is larger because it goes around in a circle with a bigger radius. The velocities of each of the toys are related to the angular velocity omega. The relationship, if you recall, is given by this. The tangential velocity is r times omega. So in this particular case, r for the smiley is larger than r for the bluish toy. Consequently, the tangential velocity of the bluish toy is rb times omega. The tangential velocity of the smiley is rs times omega. So the velocity, the magnitude of the tangential velocity of the smiley is larger than the magnitude of the tangential velocity of the bluish toy. That is important. Even though they have the same angular velocity, they have different tangential velocities. Of course, we can speak also of something at the center of our platform. You know, that nail there, for example, at the center. As the platform spins, that nail does not rotate at all. So in that particular case, I call it nail, the pin, or whatever you'd like to call it, that central pin, the velocity of that central pin is equal to 0, the tangential velocity, because the radius for that central pin is 0. Let's look at another example of this. Okay, we have the rotating Earth. Okay, the graphic here does not allow me to position things that are going to spin along with the Earth. But let's for a second assume that we have an object, a person, let's say, along the equator. Okay, let's say here, about there. So for that person along the equator, every time the Earth rotates, that person is moving around the Earth. Relative to its position on Earth, that person is not moving. But in the bigger scope of things, when looking at the Earth from the outside, that person is moving along the whole country, that's moving along the rotation of the Earth. The velocity of that person is the radius times omega. Omega being the rotational velocity of the Earth, and in this case is 1 rotation per day. Now the radius is going to depend on where that person is. To do a simplified graphic, think of this as the axis about which the Earth spins. Someone here is going to rotate with this radius. Someone here is going to rotate with this radius. Someone along the equator is going to rotate RE with that radius. The equator radius being the largest radius. Someone on the North Pole is not going to rotate at all. So in other words, the velocity of a person along the surface of the Earth is going to be given by the radius at that location relative to the axis of rotation of the Earth times omega, which is 1 rotation per day. It might be interesting for you to try to calculate what that velocity is for someone on the equator, for example. You'll be surprised by the result.